Neighborhood of a point in a topological space. This concept is quite similar to the concept of neighborhoods in metric spaces. Let X top be a topological space, X naught element of X. Also, let N be a subset of X. Then N is said to be a neighborhood of the point X naught if there exists an open set, say V, in the space X such that X naught element of V and V is contained in the set N. In this case, we also say that X naught is an interior point of the set N. Now we can also define the interior of the set N. It is defined as the collection of all interior points of N. Next is a proposition. It states that a subset of a topological space is open if and only if it is a neighborhood of each of its points. This result is a characterization of neighborhoods. For the proof, let us assume that X2 is a topological space. Also, take a subset G of X. First, suppose that G is an open subset of X. Then, for any X naught element of G, we have X naught element of G and G is contained in G itself, where this G is open in X. So we can say that this set G is a neighborhood of X naught. Here X naught is an arbitrary point of G. So we have G is a neighborhood of each of its points. Now for the converse part, assume the given condition. That is, suppose that G is a neighborhood of each of its points. Then for any X element of G, G is a neighborhood of this point X. So there will exist an open set, say Vx, since the open set will definitely depend on the choice of small x in the space X, such that X element of Vx and Vx is contained in G. This implies that singleton set X is a subset of Vx, since X element of Vx, and we have Vx is contained in G, and this is true for every X element of G. So if we take the union of these sets over all X element of G, we will get union over X element of G singleton set X is contained in union over X element of G Vx, and that will be contained in union over all X element of G capital G, which is capital G itself. This implies that G is contained in union Vx and union Vx is contained in G. Since this union of all singleton sets where those points were members of G, this union will definitely be equal to capital G itself. So we have G as a subset of this union and that union will be contained in G. So we can see that in this inclusion these two sets are the same. Hence we must have this union Vx over all X element of G must be equal to G, where we know that each Vx is open in the space X. So G is in fact a union of open sets, and we know that the arbitrary union of open sets is open. So we will have G is open in X. So we have proved that if G is a subset of X such that G is a neighborhood of each of its points, then G is open in X. We have proved the direct implication earlier. So we can conclude that G is open in X if and only if it is a neighborhood of each of its points. Now let us consider another proposition. Let X tau be a space and a subset of X. Then interior of A is the union of all open sets contained in A. It is also the largest open subset of capital X contained in A. So first of all, we will need to show that interior of A is the union of all open sets contained in A. For this, let us consider the collection of all open sets contained in A. And let us label that collection as U. Then we can see that phi belongs to U since phi is an open set and obviously phi is contained in A. So phi will be a member of this collection. This implies that the collection U is non-empty. Now let us consider the union of all members of the collection U, and let us label it as capital V. Then V is equal to union of all G, where G element of family U. Then we need to show that this V is equal to interior of A. To prove this, we can show that V is contained in interior of A and also interior of A is contained in V. Consider an arbitrary point, say X, from V. Then from the definition of V, since V is the union of all members of family U, X will belong to G for some G element of family U, and since G element of family U, G will be contained in A. Since U is the collection of all open sets contained in A, this shows that there exists an open set G such that X element of G and G is contained in A. This implies that this X is an interior point of A. Or we can say that X belongs to the interior of A. So we have shown that every point of capital V belongs to interior of A. Therefore, we can conclude that V is contained in interior of A. Also, if X element of interior of A, then from the definition of interior of A, we can say that there exists an open set, say H, such that X element of H and H is contained in A. So we have an open set H which is contained in A. This must imply that H belongs to our collection U. Since we have defined V to be the union of all members of the collection U, and since H element of U and X is a member of H, we can say that X belongs to the union of all members of the collection U, which we have labeled as capital V. So we have proved that all points of interior of A belongs to V. Therefore, we can conclude that interior of A is contained in V. We have already proved that V is contained in interior of A. Combining these two inclusions, we get V is equal to interior of A as required. Thus, we have shown that interior of A is the union of all open sets contained in A. Now, it remains to show that interior of A is the largest open set of X contained in A. We have already proved that interior of A is the union of all open sets contained in A. This means that interior of A is an arbitrary union of open sets, and we know that arbitrary union of open sets is open. So we can see that interior of A is open in X. Now we need to prove that interior of A is in fact the largest among all open sets contained in A. For this, let us consider an open set G contained in A. Then from the definition of our collection U, we can say that this G belongs to the collection U, and hence interior of A is in fact the union of some open sets including this G. So we can say that interior of A will contain this G, where G is any open set contained in A. So we can see that interior of A is in fact the largest open set contained in A. Corresponding to a topological space, we can define an operator I from P of X to P of X defined by I of A is equal to interior of A, where A belongs to P of X. Since we know that interior of any subset of the topological space X is well defined, we can define a function, an operator from P of X to P of X using this definition. This operator is called the interior operator associated with tau. The properties of interior operator are dual to those of the closure operator. Exterior of a set is defined as the interior of its complement, that is, exterior of A is defined as the interior of the complement of A, that is interior of X minus A. Let X tau be a space and let X be a member of capital X. Then Nx be the set of all neighborhoods of X in capital X with respect to tau. Then Nx is called the neighborhood system at X. In the following proposition, we list some properties of the neighborhood system. Let X tau be a space, and for X element of capital X, let Nx be the neighborhood system at the point small x. Then if capital U element of Nx, then X will be an element of U. Second property states that for any U and V element of Nx, U intersection V belongs to Nx. Third property states that if U element of Nx and V contains U, then V is also a member of Nx. Fourth property states that a set G is open in X if and only if G belongs to Nx for all X element of G. And fifth property states that if U element of Nx, then there exists some V from Nx such that V is a subset of U and V element of Ny for every Y element of V. Most of these properties are obvious from the definition of neighborhood itself. For the proof, let us consider Nx, the neighborhood system at X, which is defined as the collection of all subsets U of X where there exists an open set G, that is a member of tau, such that X element of G and G is contained in this U. Now, to prove the first property, if U element of Nx, then from the definition of neighborhoods, there exists an open set, say G, such that X element of G and G is contained in U, which obviously implies that X element of U as required to prove the first property. Thus, we have proved that if U element of Nx, then X belongs to U. Now, consider the second property. For this, let us assume that U and V are two members of Nx. Then we need to prove that their intersection, that is U intersection with V, is also a member of the neighborhood system. Since U element of Nx, there exists an open set, say G, that is a member of tau, such that X element of this G and G is contained in U. Similarly, since V belongs to Nx, we can find another open set, say H, that is a member of tau, such that X element of H and H is contained in V. Thus, we have two relations. X element of G and G is contained in U, and similarly X belongs to H and H is contained in V. If we combine these two relations, we will get X element of G intersection with H, since X element of both G and H. And since G is a subset of U and H is a subset of V, we can write G intersection H is a subset of U intersection with V. And here we know that G intersection H being the intersection of two open sets is open. Thus, we have showed that X belongs to an open set and that open set is contained in U intersection with V. So, we can say that U intersection V is a neighborhood of X. Or in other words, U intersection V belongs to the neighborhood system at X. Thus, we have proved that whenever U and V are members of the neighborhood system, their intersection, U intersection V, is also a member of the neighborhood system Nx. To prove the third property, let us assume that U is a member of the neighborhood system and that V is a superset of U. Since U element of the neighborhood system, that is, since U is a neighborhood of the point small x, we can find an open set, say G in X, such that X element of G and G is contained in U using the definition of neighborhoods. And since U is a subset of V, we can see that there exists an open set G in X such that X element of G and G is contained in V. So, applying the definition of neighborhoods again, we can see that V is in fact a neighborhood of X. Or we can say that V belongs to Nx. Thus, we have proved that whenever U is a member of the neighborhood system and V is a superset of U, the superset V is also a member of the neighborhood system. So, we have seen that the supersets of every member of the neighborhood system belongs to Nx. Now, to prove the fourth property, that is, we need to show that a set G is open in X if and only if G belongs to Nx for every X element of G. First of all, let G be open in capital X. Then for every X element of G, we can see that X belongs to G and G is contained in G itself, where this G is open in X. So, this implies that G is a neighborhood of this point small x, or in other words, G belongs to Nx. And this is true for every X element of G. And conversely, let G be a set such that G element of Nx for every X element of G. G element of Nx implies that there exists an open set, say Hx, such that X element of Hx and Hx is contained in G, since G is a neighborhood of X. And this implies that G is in fact the union of all such Hx. Thus, G is the arbitrary union of open sets and hence it is open. Thus, in the converse part, we have proved that if G is a set such that G element of the neighborhood system for every X element of G, then G is open in X. Combining these two results, we can conclude that G is open in X if and only if G element of the neighborhood system Nx for every X element of G. Now, it remains to prove the fifth property, that is, we need to show that if U element of Nx, then there exists a V element of Nx such that V is contained in U and V belongs to Ny for every Y element of V. Let U element of Nx, then U is a neighborhood of X and hence there exists an open set, say V, such that X element of V and V is contained in U. Since the set V is open, we can apply the fourth property to V and we can say that V is a neighborhood of each of its points. Therefore, for every Y element of V will be a member of the neighborhood system at that point. Therefore, in particular, V element of Nx also, since X belongs to V. So, V will be a member of Nx. Thus, we have proved the existence of the set V such that V element of Nx, as we have seen here, such that V is a subset of U, as we have proved here, and the element of Ny for every Y element of Z, which we have proved here. Thus, combining all this, we get the required result. Thus, if U element of Nx, then there exists a V element of Nx such that V is contained in U and V element of Ny for every Y element of V. And V is a member of Nx also. Thus, the proof of property 5 and hence of the proposition is complete.